Hello and welcome back to another YouTube video, and in this video I'm gonna talk about a problem on LeetCode for deletion of node in a binary search tree and how can we do this. So in order to delete a node, it's simple, but it's not the simplest. So we need to crack down the process of how we can delete it. So I made conceptual design for this problem, and let's see it. Alright, so what are the cases for deletion in binary search tree? We can delete a leaf that contains no children, or maybe we can delete a node with a single child. Maybe we can delete a node with two children. Maybe we can delete non-existing node. So those are the most frequent cases which you will probably hit. And let's start by deleting a leaf. So now we want to delete 30. How can we find this 30 at first? We need to use the searching algorithm of binary search tree. Let's remove this title and start solving. Let's search for the value 30. Is 30 greater than or smaller than 10? It's greater. So now we move to the right. Now we ask the same question but to node 27. Is 30 greater than or smaller than 27? It's greater. So now we move right. We have found our element 30. So what should we do after we have found our element? So now, since it's a leaf and it contains no children at all, so we can basically just eliminate it directly and ignore it completely and replacing it by a null value. By replacing it by null value, then this pointer points at null, which basically removes the element. And that's really the simplest way to remove a node in binary search tree. So now what happens if we have a child and we want to remove a node containing that child? So let's see, remove the title, and we will need to find this node at first, so we need to use a searching algorithm of binary search tree. Let's ask, is 7 smaller than or greater than 10? It's smaller than. Now you ask the same, is 7 greater than or smaller than 6? It's greater than. We go to the right. Now we ask, is 7 greater than or equal or smaller than 7? It's equal, so we found our node, but we find that it has an element. It has one child. So how can we fix this problem by deleting 7 without destroying our binary search tree or making the correct solution? To be honest, I think the best solution is kind of straightforward. You just eliminate this node by moving the right pointer of its parent, which is 6, to the child of to be removed node. So basically the right pointer of 6 will be pointing at 9, and we will just ignore this 7, redirecting its parent to the child. So after removing it, and it will be the same look like this, and it will be holding the binary search tree property with no problem. That's it for the single child. What happens if we have a 2 children node and we want to remove that node? So in order to remove this node, we need to first find it. So we ask the same question, is 6 greater than or smaller than 10? It's smaller than. We move it until we find this, move left, and now we have found our node. How can we remove 6 without destroying our binary search tree property? So we need to choose a child, but how can we choose a child here? I'm gonna remove this right side so it's kind of more focused on this subtree. Alright, so what are the properties of binary search tree so we can make a good decision about which child to take? So we know that left child of a node is always gonna be smaller than the parent, and the right child will be always greater than its parent. Alright, now that's a property of binary search tree. So how can we find a child that doesn't violate our binary search tree property? So how can we do this? I will give you a couple of questions as a hint so we can understand how can we choose a child. First question, what number would be the closest to 6 if we went to the left? You can stop the video here, I will be answering now. If you went to the left direction, that means any child at this node or subtree will be always smaller than 6. So any node here will be always smaller than 6. So I want to find the highest node in this tree, subtree, that is less than 6. And I can make sure it's less than 6 because it's a binary search tree that has property that left child will be always smaller than its parent. So how can we find the largest child in this subtree? By going to the right direction. So from 2 we need to go to the bottom right to find the highest possible value in that subtree, which in our case is 3. So now this is the approach if we went to the left. There is also another question. What number would be closest to 6 if we went to the right direction? I will be answering now. If you want to see the answer, keep going. Alright, so if we went to the right direction, we know that the right subtree is always going to be greater than its parent. So we know any value or any node in this subtree will be always greater than the parent, which is going to be 6. So we need to find the smallest value in this subtree that we know of, or because of the property of binary search tree, is always gonna be greater than 6, but we want it to be the closest, smaller than 6, but we want it to be the closest to 6. So how can we do this? So basically we know any value at the right side is always gonna be greater than 6, but we want to be the smallest value in the right subtree, so it is the closest to the value of 6, which we want to be removed. So another question, how can we find the smallest value in the right subtree? By going completely to the bottom left direction. So there are two statements, you can understand it. For finding this solution, you will either go to the rightmost of the left subtree, or you will be going to the leftmost of the right subtree. It's one way. You can choose this approach or this approach. Both of them work fine. There is no problem. So how can we do this? Solve this problem? So now let's say we go to the left direction. Now we have went to 2. Now we need to find the rightmost of that left child, which is gonna be 3. So we're gonna replace that 6 by that 3, and now after replacing them, I'm now showing you my approach. I'm going to the left, which is 2. Now I'm going to 3, and now we have found our rightmost. Now we're gonna replace this 6 node, which we want to delete, with our 3. And now we have a correct binary search tree which doesn't violate our property. Alright, let's see another example. If we went to the right direction, how can we solve this problem? We know if we went to the right direction, we need to find the leftmost child of the right subtree. So right subtree starting from 7. Now we need to find the leftmost. There is no leftmost at the right subtree. So what should we do? We should take the 7, since there is no left child. So now we just move the 7 up there, and now we have a correct binary search tree. two approaches, both of them work fine, there is no problem with them. So that's it for this problem, and now let's see the complexity for this solution. If you're going to use an iteration approach, the space complexity will be O of 1 and time complexity will be log n, where n is the number of nodes in the whole tree, and you can calculate the math yourself. It's just the same as searching algorithm. But there is downside for iteration. You will have a couple of edge cases which you will need to make sure you fix to make an efficient solution. Recursion approach is a bit less efficient because it's using a memory stack for space complexity. So its memory its space complexity will be O log of n, and time complexity of log n as well, where n is also the number of nodes. And recursion is more cleaner code, to be honest, but it's less efficient. So it's a trade-off, and you can discuss it with your interviewer if you want to be using more efficient approach like iteration, or maybe if you are allowed to use recursion. And that's it for this problem, and now let's get into code.